All right. So on Tuesday, we talked about a little bit about thermodynamics and all this good stuff. I don't think any of it, I don't think you need to know any of it for this lecture. That was kind of its own standalone thing. If you haven't watched it yet, go watch it or not. Today we're talking about a little bit about fluid mechanics, a little bit of background, and mostly focusing on how, the converging diverging nozzle works in a rocket engine and how it can achieve supersonic speeds. I have this little quote here because, I mean, this is the part, at least, that I was always interested in when I started LRE. So I'd always ask, why supersonic flow at the exit? And no one really had a good answer to that. So we asked one of our professors, Media Betty. We asked him how it works, and he basically just told us to go take his grad class on fluids. So yeah, it is a very complicated subject, and hopefully I've been able to explain it relatively clearly. All right. So first, a little bit of background on fluid dynamics and incompressible flow, which is mostly what we focus on at Northeastern in undergrad, and I think grad too might mostly deal with incompressible flow. Incompressible flow is any flow where the density is constant. So most liquids are considered incompressible. And actually most gases, while they can actually be compressed, most gases flowing at low velocities can be thought of as incompressible. We're going to talk a little bit about that, I think, on the next slide, actually. So basically, we'll look at a converging diverging nozzle with an incompressible fluid. So in fluids, a converging nozzle is just called a nozzle. A diverging nozzle is sometimes called a diffuser. And basically, with incompressible fluids, fluid flows in, and in the converging section, it'll accelerate, and in the diverging section, it'll decelerate. So in order to explain that mathematically, we have this equation right here called the continuity equation. You guys may have seen this before. It's pretty much just m dot equals rho AV, mass flow rate equals fluid density times the cross-sectional area of tubing times the fluid's velocity. So basically, this is called the continuity equation because generally in a fluid flow at steady state, m dot and rho AV are considered constant. So in this equation, if you go ahead and rearrange all these variables, so in an incompressible fluid, you have density, rho is constant. We already said mass flow is constant. We're going to be looking at this in the steady state. So m dot over v is a constant, and then area times velocity also must be constant. So that means that with incompressible flow, the cross-sectional area and velocity have an inverse relationship. If area increases, velocity has to decrease. Area decreases, the velocity will increase. So that's why, as I said before, in a converging nozzle with incompressible fluids, the flow will accelerate, and in the diverging section, it will slow back down. But this is just for incompressible flow. For compressible flow, so for incompressible flow, remember we assumed that rho density is constant, so we could say that AV is constant. With compressible flow, you can't say that anymore because mass flow rate here is the only one that's constant. Density can change, area is changing. So this kind of makes the relationship a little more complicated. We have three variables, or at least we have, if we're varying area, then we have two variables. It's an impossible from this equation to know what's going to happen, whether density change or velocity change is going to be more dominant. So for incompressible fluids, we need a different equation to address this. So for compressible flow, as I said at the beginning, for gases that are technically compressible, if they're flowing at a low enough speed, you can pretty much just consider it incompressible. But these gases will behave differently depending on the speed. So that's why we use something called the Mach number. So Mach number, if you remember, is basically the ratio of the fluid's velocity to its the speed of sound through that fluid. It's basically a non-dimensional number that we use to characterize pretty much how the flow is going to behave. And you'll see that on this chart, graphic, I don't really know what to call this. But right here, you can see we have different regions for different Mach numbers. So below a Mach number of 0.3, you can assume the flow is incompressible. And even though we have a compressible fluid, for Mach numbers less than 0.3, we can use this equation. This equation is valid. Once you get past Mach 0.3 and approach Mach 1, you get in the subsonic flow and transonic flow. We'll go into that more on the next slide, but basically, this equation isn't valid anymore. You have to use a different set of equations. Basically, that's all this is. The Mach number helps us categorize and figure out which set of equations we have to use. Also, just for reference, here are the equations for the speed of sound through the fluid. The speed of sound is also known pretty much just as the speed that pressure waves propagate through a fluid. Remember, sound is basically just pressure vibrations and pressure waves. So we call it, sonic velocity. Here's two different ways of calculating it. Both are fairly similar. I think you just, ideal gas law can rearrange some variables. So square root K, specific heat ratio, R, the specific gas constant, and the fluid's temperature. You can also calculate it based on pressure and density. Are there any questions on Mach number, sonic velocity, all these different flow regimes, as they call them? All right. So, as I said, for each of these different regimes here, you have a different set of equations to use because they all behave differently in those different regions. So, this very scary looking ugly equation is the same continuity equation, but for the transonic and subsonic regions. So this is pretty much the same equation here, except for a different for flow moving this speed. And this is actually derived from this equation, and I believe some of these ideal gas relations we talked about on Tuesday. Basically, you take the original equation and substitute, instead of just having a term for density, you basically sub in density in terms of the stagnation pressure and stagnation temperature, and then use the velocity term as Mach number. So basically what you would do is find an equation that describes the density based on the fluid properties that are present at that moment, and substitute those in for this term here, and then just sub in Mach number for velocity there. And that's how you get this big, ugly equation. And this is the equation that applies to rocket engines. Rocket engines are decidedly compressible flow. We have gases, and they are flowing in the transonic, supersonic flow regimes. So this is the equation we use to describe flow through rocket nozzles. Are there any questions on that before I move on?
I had a quick question.
Yeah.
Does this apply to like supersonic flow as well?
I believe it does. I believe
It does. It applies for supersonic. It starts breaking down for hypersonic because stuff gets weird there. But you'll see that. Can you just go back to that slide, Jackson? Yeah. Basically, if you try to set let's say that you have everything else constant and you try to find a Mach number here where you know everything else, you're going to find that it's a parabola. So you'll have two answers for the Mach number, which is where you get the shape of the converging diverging nozzle from, because for any given area, basically, you can have two different Mach numbers. One is when it's converging and one is when it's diverging. And so one of them will be below one will be above one.
Yep. And we'll actually see a similar graph right here. Yeah. So this graph here is basically this equation graphed. I believe. What did I do here? So this is Mach number is on the x-axis, cross-sectional area is on the y-axis. So I think what I did is, I just took this equation and moved everything other than area to the other side, and then graphed that as a function of Mach number. And everything else here, this pressure, this temperature, gas constant, all this stuff I kept constant. And I actually think I used the values of those from the regen engine. So as Arun was just saying, this is, you get a parabola. So for every area, there are two Mach numbers. And basically we see that so this is, this point here is at x equals 1, at a Mach number of 1 is where that parabola has a minimum. So that means for Mach numbers that are less than 1, you have the relationship such that as area decreases, Mach number will increase. They have an inverse relationship, just like back for compressible flow. I think you can even see basically when you transition between these regimes, you would just put a tangent line here. So this is the original concept. Let me draw this out. So if you put a tangent line here and say this is 0.3, this is the original equation, continuity equation we used, and then here it transitions to the one I showed on the last slide. But anyway, so this continues the inverse relationship between area and velocity or Mach number up until you get to Mach 1. And that's where things get weird. And the Mach number and area then have a positive relationship. As you increase the area, Mach number also increases. And that's mathematically what's happening in the rocket engine nozzle. Although mathematically is kind of, theoretical, it's kind of out there. You still don't really know what's going on. So I'm going to explain it in kind of more like a intuitive way later on. But also before we get there, I want to highlight the fact that, at this minimum where Mach number equals 1, at the minimum of a parabola, it doesn't have a positive or negative slope. It's kind of just there. Derivative is 0, which means any further decrease in area isn't going to increase the Mach number anymore. And so that's the concept of choked flow. I think Arun and I have mentioned this before, but the converging section of the nozzle can't accelerate the flow any faster than Mach 1. And this is why. Once you get to the bottom of this parabola, any further decreases in area, you're not going to see any change in Mach number. So, a little more about this concept of choked flow. As I said, at Mach 1, the flow is choked. Mach number can't increase anymore. So what actually is happening there? So at Mach 1, remember, this is when the velocity of the fluid is the same as the speed of sound or the speed that pressure waves propagate through the fluid. So the fluid is flowing at the same speed that pressure waves are flowing through it. So once you get to Mach 1, any variations in pressure, it can't travel back up the flow and affect the flow upstream in the nozzle. So because flow rate is driven by a pressure gradient, a pressure drop, so a higher pressure at the nozzle inlet, and then that kind of forces it to the lower pressure at the nozzle outlet. And then because of this, the Mach 1 is traveling the same speed that differences in pressure will travel through the stream. The flow is independent of any changes in the outlet pressure or just any changes downstream. It's only dependent on the upstream conditions. So we say it's choked by the upstream inlet conditions. Now that explanation can kind of be a bit confusing, so I'm going to try to, again, explain this concept more intuitively. So to kind of picture what's going on, consider you just have like a pipe with a converging nozzle at the end. So fixed inlet conditions that exist inside the pipe, and the nozzle is of a fixed geometry. And now you start decreasing the outlet pressure, kind of the environment pressure. You still have the same inlet conditions inside the pipe, and you bring down the pressure at the outlet. What happens is the pressure gradient you've just created, starts to drive a mass flow rate. And as you decrease that outlet pressure, it's going to drive more and more mass flow rate until you hit Mach 1 at the nozzle exit. Now, once you do that, as we said before, since the flow is now traveling at the speed that pressure flow, it's the speed that pressure waves travel through the fluid. We can kind of picture it as like as changes in pressure flowing through the fluid in the opposite direction. So once you hit that Mach 1, any changes downstream are not going to affect anything that's happening inside the nozzle. So you can then go and decrease that outlet pressure as much as you want, all the way down to a vacuum. But it's no longer going to increase the mass flow rate or the Mach number of the flow. So that's kind of just the concept of choked flow. Basically, it's called choked flow because only the inlet conditions are affecting the flow rate. Only a change in the inlet conditions will end up changing the flow rate, or you won't actually change the Mach number. If you increase the pressure, basically all it'll do is it'll increase the density of the flow, but it'll still be the same Mach number. So basically in rocket math, conditions at the choke point of the nozzle are usually given a star superscript. So T star is temperature at the nozzle choke point, P star is pressure at the nozzle choke point, and A star is usually the nozzle throat area. Are there any questions about choked flow?
I guess I had one question about it. If you said this was only dependent on inlet conditions now?
Yeah.
So if you were to like increase some of the inlet conditions, could you get it over Mach 1?
No, so you can't get it over Mach 1. But remember, the speed of sound and the Mach number are dependent on properties of the fluid. So here it's based on temperature. It can also be shown based on pressure and density. So it's kind of weird to think about. You can actually increase the velocity, but that's only because you're also increasing the speed of sound through the fluid. So basically, as I said, if you increase the inlet pressure, you can increase the mass flow rate through the nozzle because the density increases. If you somehow hold the density constant and increase the pressure, you can actually increase the velocity of the flow through that nozzle, because you see here pressure is in the numerator of the sonic velocity term. So the denominator in the Mach number will increase, but since the Mach number is still 1, that means your flow velocity will increase. I know that's kind of weird to think about because usually you can just kind of say that Mach number is directly related to velocity, but in this case your Mach number is constant, but the velocity can still increase, if that makes sense.
Yeah, that makes sense. Thank you.
Yeah. All right. Now for the fun part, the diverging section of the supersonic nozzle. Yeah, this is like one of the one slides I think we changed from the summer. I think I have a better explanation of it now. So anyway, as I said before, when your Mach number is around 1 in the transonic flow regime, flow is acting compressible, so density will change. So this means you're thinking about it's from the previous example of you have the flow through the pipe and then converging nozzle. As soon as it exits that, ambient pressure will decrease, its density, it can expand, density will decrease. And think back to all the way back to this continuity equation. So you have constant m dot, density is decreasing, area and velocity are variable here. So in the example with the just the converging nozzle, you're dumping the flow into ambient conditions. It can expand to whatever area it wants. So as the density decreases, area increases, velocity, that depends on how much it expands. If it expands a lot, if the cross-sectional area increases a lot, the velocity will actually decrease. But if the density goes down and the area goes up a little bit, the velocity can increase a lot. And that's how we kind of shape the nozzle to get this increase in velocity. It's mostly coming from a decrease in density, since the pressure at the outlet is lower. Next slide. Yeah. So to think about kind of what's happening in the diverging section of the nozzle. So now we have that same example where we have the converging nozzle and we have our choked flow. So now put a diverging section of the nozzle on there. So, actually, another thing to keep in the back of your mind while we're talking about this is Bernoulli's principle. Hopefully, all of you guys have seen that in physics. Basically, it just says that as the velocity of a fluid increases, its pressure decreases. You don't really need to see the equation. It's just kind of remember that relationship that as velocity increases, pressure decreases. So at the choked conditions, we have the pressure at the throat of the nozzle is either equal to or less than the exit pressure. So once it leaves the nozzle, there's no drop in density. Flow just starts slowing down. Yeah. But as you begin to drop the exit pressure below the throat pressure, that flow has room to expand. It goes from a higher pressure to a lower pressure. Basically from the definition of pressure, it's the force being exerted on whatever is containing it. There is nothing containing it anymore. The ambient pressure in the nozzle is now less than the pressure of the fluid, so it can expand out and stick to the walls of your diverging nozzle. And in the rocket nozzle, I think we kind of just designed the nozzle so that the way that this relationship works out, the density decreases more significantly than the area increases. So you have this velocity term increase. So yeah, even though all your flow conditions are kind of choked by upstream conditions, we can control the pressure that the flow is kind of flowing into and is being bound by. So here, as you decrease the the ambient pressure, the more you do that, the more the flow is going to fill the nozzle, and the density is going to decrease as it expands, and the velocity term is going to increase. This is kind of better explained by looking at this graph. So you'll see here, basically you have your P inlet, and at the start of this kind of like thought experiment, you have the same pressure in the entire system. And then you start to drop this pressure. And if you don't drop it quite enough, you'll just get it speeds up and pressure goes down. Remember Bernoulli's, and then the nozzle acts as a diffuser since it hasn't hit Mach 1, and then the flow slows down, pressure increases again, and then you keep dropping it further. You get to choked flow at the nozzle throat, and what can happen is the fluid kind of just stays the same velocity, or it could reverse back to a diffuser and slow down again. You keep dropping this pressure and allowing it to expand into the nozzle, and you get the combustion gases to accelerate. If you haven't dropped the exit pressure enough, it can separate from the nozzle walls. And then you keep dropping this and it'll stick to the nozzle walls and you have the full combustion flow through the nozzle. Are there any questions on that? Or Arun, do you have any comments that might clear that up?
Not particularly. It's just really messy to try to explain this part. It's like,
Yeah, this is a very complicated concept to explain. I'm trying my best. I changed the whole explanation from what we did over the summer, trying to find a better one. But hopefully that was clearer than at least what we did over the summer. And hopefully you kind of have an idea of what's going on. But please ask questions if you don't. I think the basic concept is that with supersonic flow, let me go back here. The basic idea is that with supersonic flow, density is quite variable, and as you increase the cross-sectional area, as long as the pressure there is low enough that it will expand and fill the nozzle, and you're constraining that area with the nozzle, the density is going to decrease and the velocity is going to increase orders of magnitude larger than the change in cross-sectional area, given the constant mass flow. And I think here are some more graphs that honestly I think are kind of confusing. Arun, you're the one who included these. Do you have any comments, or should we just keep going?
let's skip this for now.
Yeah. Okay, so let's see. As always, we make assumptions, and there are limitations to those assumptions. I think this slide is kind of less in depth than the one for the first one, because it's a lot of the same assumptions. So we assume ideal gas when we're doing all these flow stuff, especially since this equation, since we're plugging in a relation to find density, assumes that you have an ideal gas. But no real gases behave ideally. We can use this to get close enough and usually make it work, but there is still some uncertainty there. It's not going to behave exactly as the math says. And again, the relations that we used to derive this ugly equation also assumed isentropic, no entropy generation, no entropy transfer. So that's just another way that it's not quite accurate, because no actual process is entirely isentropic. So again, those relations will be slightly off, but usually will be close enough.
Another assumption I forgot is we assume that the specific heat ratio is a constant for a given gas. That's not quite true. It's technically dependent on both temperature and pressure. It's a lot more dependent on temperature than pressure. But you're talking about, like, for example, air. It is going to go from 1.4 to like 1.3 when you go from room temperature to about 4,000 Kelvin. So we can mostly approximate it and assume it's constant when we're deriving these equations. But when you actually, like when they're doing big rocket engines, they do it kind of numerically with it changing constantly there. There's a couple other ones like that, but where that's the case.
Yep, that's the last slide in this section. I think over the summer we combined these two parts 2 and 3, but I'm just going to stop here. This is a lot to take in, and yeah, does anyone have any questions about anything that we covered today? All right. I'm just going to go ahead and end this meeting since I have to use the bathroom.
We will meet again on Tuesday to finish up the last section of this.
Yep. Also, I put it in the announcement today, but if you guys want your rocket engine printed, it should just like have a little desk toy. You can go ahead and send me and Arun the CAD file. Our emails are in that Discord message, and we'll scale it down for you and print it out. And if you're on campus, you can come pick it up either at the end of this semester, or the beginning of next semester, if you're here doing the interterm thing or whatever. We haven't thought about mailing it to anyone, but I'm sure we can make accommodations if anyone really wants theirs.
We'll also on Tuesday be talking through the plans for next semester, with hopefully building at least one of the engines you guys designed. But whatever we talk through, we will also write up and post for people who can't make Tuesday's meeting, because I know we're coming into the end of the semester and everyone is super busy.
Yep.